All right, so let's just get concluding with this quite lengthy chapter of the lecture notes. There are two sections, this 1318 and 1319, which I am not going to go over the synchronous video because it would be just too long. That's the discussion on the Boltzmann factor and the re-derivation of the Maxwell-Boltzmann distribution. These two things, you can do it only knowing what's the equilibrium occupation of any given phase space cell. Okay, so you just have to make assumptions on what the energy of every phase space cell is going to be. Okay, we have already discussed that the difference in the equilibrium occupation between any two states of the system, and by state here I mean phase space cell. Okay, that's the association I make. Phase space cell. So the difference in occupations between any two cells is going to be is going to go like exponential, of minus the energy difference between these 2 points. So it would be, let's say, Ji. Okay, so let's say this is the difference in occupations between J and I, 2 different phase space cells, and here this thing divided by kT. So whichever is the relevant energy scale that tells apart the energy of cell J and this energy of cell I that I'm comparing it against, so that energy change you have to divide it by the thermal excitation energy, kT, and take the exponential of minus that, and this gives you the proportion, the relation between the equilibrium occupations of the two things. Okay, that's the general idea, but you have it all worked out in the lecture notes. Okay, and what I do want to elaborate on a little bit is actually very important. So this is the single particle partition function. Okay, so the partition function, and what can we calculate with the partition function? Okay, partition function. So usually you denote this by set, and set 0 is defined as the sum from 1 to m, so all the states of your system, or all the, if you like, the classical kind of Boltzmann language, all the cells in the single particle phase space of my non-interacting many component system. So this is the sum of e to the minus beta ei. Okay, that is the thing that I'm going to call partition function. Okay, so in particular, remember that n, right, is the sum over all cells from 1 to m of the occupations. Okay, and the occupations were nothing but this thing times e to the minus alpha. Okay, so one thing that is an identity is that e to the minus alpha times the partition function, which would be the sum of these terms here, equals the total number of particles. Okay, so now is when we interpret this alpha term. Okay, so it's related to this partition function per particle. Okay, so if you like, you can do this: e to the alpha, okay, equals set 0 divided by n. Okay, and you could take logarithms here if you like, and you say that alpha equals the logarithm of this thing. Okay, so this is actually, keep this in mind because we are going to use it in a second, this identity. And just by looking at the form of this term, really, okay, we see that we can calculate a lot of useful things only knowing this sum. Okay, so when you have a problem in statistical mechanics, usually what you want to do first is to calculate the partition function. If you can calculate this sum explicitly, so if you can just write it down in terms of the energies of the different states of the system and the temperature that you know your system has, then just from this object you can calculate internal energy, entropy, free energy, and pressure. So you can calculate everything really of your system. So let's see how you do that. It's actually quite straightforward. So okay, so for the energy, remember we already saw this. Okay, so remember what this is: sum over the states of e to the minus beta ei. Okay, so we already saw that when you take the derivative with respect to beta of the logarithm of this object, which we didn't give it a name before, but it is the partition function. So if you do that, remember what we got in the explicit calculation when we did this calculation, yes, 2 videos ago, right? What we got is the internal energy per particle. Okay, this is an identity that we showed. So I just think about it and you see that we already did that. So the internal energy of your system is actually minus, well, it's n times, let's say, minus n times the partial derivative of the logarithm of the partition function with respect to the inverse temperature. Okay, so that is a result. If you have set 0, you can take this derivative, where remember beta equals 1 over kT. Okay, and then you get the internal energy. Fine. So then what else can we do? Now remember what the entropy was. Okay, so the Boltzmann entropy in equilibrium, we said it was the Boltzmann constant n logarithm of n. Then it was alpha times n, and then it was beta times u. Okay, so let's just write out what each of these things is. This is n logarithm of n. Alpha. What is alpha? Remember what we just said. Alpha is the logarithm of set 0 minus the logarithm of n. Okay, so what we have here is n times the logarithm of set 0 minus the logarithm of n. Okay, and here is plus beta, the internal energy. Okay, so this guy will go with this one. And what you have in the end is that this is k and n logarithm of set 0. That's the term that survives down here. And this is beta u. Okay, and u itself can be exclusively calculated from the partition function. So again, if you know the partition function, you can first calculate energy. Once you have energy, you can put it here and calculate entropy. Okay, so that's a nice thing about it. Now, what other things can you calculate? Well, remember what the free energy is. Free energy is a Legendre transform of the internal energy in which you are swapping the variables t and s. That's what it is. Okay, so again, you know everything from the partition function. You know that this guy can be found from the partition function, and you know also that the entropy, in this case Boltzmann entropy, which we have hopefully convinced ourselves that at least for a non-interacting system is equal to the true thermodynamic entropy. So what this is the internal energy minus 1 over beta k SB. Okay, and just replacing what SB is from here. So that is u minus 1 over beta k times k and log set 0 plus beta u. Okay, so what do I get here? The k goes away with the k, the beta goes away with the beta, and then this means that the u goes away with the u because they have different signs. And what I'm left with in the end is minus 1 over beta. This went away already, yes. And here I have the logarithm. Wait a second, because I'm missing something. No, that's correct. So this logarithm of set 0. Okay, so that's just the free energy of my system. And there's another thing we can calculate, and this is remembering what the conjugate and the natural variables of the free energy are. So remember that free energy, if you take the differential of it, what you get is minus s dt. So one of the natural variables is temperature, and the other one is still volume, PdV. Okay. So what this just I want to say is that the partial derivative of the free energy with respect to volume, okay, at constant temperature, with a minus sign here, is just the pressure. Okay, but we have written already what the free energy is in terms of the partition function. So we just have to take the partial derivative of that guy with respect to the volume. Okay, so what is this? Well, this is n divided by beta, partial derivative of the logarithm of z0 with respect to the volume. Okay, so that thing gives me the pressure. Okay, just simple like that. So these are the expressions to remember: what pressure is in terms of the partition function, what free energy is in terms of the partition function, what entropy is, and what internal energy is. Okay, so the whole point is when I'm given a system and I'm told, well, I could be told many things, okay, but usually I'm given a system which is made of individual quantum components, and I know that these individual subsystems, which are independent and make up a large number of them, make up my thermodynamic system, they can exist in a number of states. Okay, and these states I am given the energy, so energy 1, energy 2, up to energy m. Okay, so any number of them. If I know these energies, it's trivial for me to calculate explicitly this expression. It could be more or less lengthy, the expression, but it's just a sum from 1 to m of e to the minus beta and each of the energies that I am supplied with. Okay, so that's how I get this function, the partition function, and just differentiating the logarithm of it, taking logarithms, manipulating it in these ways of these formulas that I showed here, you can get pressure, you can get equilibrium, free energy, you can get entropy, and you can get internal energy. Okay, so that's why it's really convenient to work in statistical mechanics, the partition function. And this finally concludes this chapter. So I will just leave you for the next one. Remember, the next one is closely related to this. We are simply going to calculate statistical weights of macrostates in the case in which we have identical particles, like we did here, but particles that we cannot distinguish from one another. Okay, so we are going to see what little changes we have to do in the statistical weights and what the consequences are.